So today we're going to look at chapter 16.2. This is like our last chapter that we're going to be looking at. Is something called the chi-square distribution. The chi-square distribution mainly looks at the difference between observed values and expected values. So whenever we say, okay, I expect the outcomes of this particular experiment to be this many, but instead, when I've observed it, I've seen that it is actually this many. Can we actually look at the distribution of this? Can we conduct a test to see if, in fact, what we expect to happen and what actually happened are close enough together? It's kind of like an extension of what we've looked at before, but now we're going to have more than two outcomes in most cases. Okay. So, first thing I want to talk about is something called the multinomial probability distribution, because this is basically what all of this is based off of. The multinomial probability distribution, this is just an extension of our binomial distribution that we've looked at before. If you remember, with binomial distribution, you always had two outcomes, success and failure. With multinomial distribution, you actually have more than two possible outcomes in each trial. But the probability of a particular outcome is the same in every trial. So you always have the probability from trial to trial for each one of these outcomes remains the same. Okay, so it's an extension of binomial. But with more than two outcomes. And it has a constant probability for each outcome between trials. Okay. So the probability of an outcome actually happening doesn't change from trial to trial. That probability remains the same. Okay. To conduct one of these chi-square goodness of fit tests, where we are going to compare the observed and expected number of this particular outcome in each experiment, when you conduct this test, it's going to be very much the same as before. It's a hypothesis test. Okay. Just as a heads up, whenever you see chi-square, it's actually, when you see it written down, they actually use the letter chi. So it's a chi-square distribution. But now we're going to have, with a chi-square distribution, again, we're going to be conducting a hypothesis test, and I'll go through the steps. But this time you're going to have like a different test statistic, because we're no longer dealing with normal distribution or binomial distribution. We're now dealing with something that stems from a multinomial distribution, which means that you may have more than two possible outcomes, which means that the probability of each outcome is not going to be exactly what we thought it was before, because we're dealing with a different distribution, so our test statistic is going to be different. That means our critical value may be different because we're dealing with a different distribution, so we're not dealing with the normal curve anymore. So all this stuff, it's going to be very much the same process, but how you figure out each one and the equation for each one is going to be different from before. Now I'm going to go through the long way of doing this with the 5-step process that we've talked about before, but just a heads up, all of this is going to be done on a calculator. There's a couple of things that you're going to have to look up in either a table or to do something very quickly by hand, but most of this is just going to come straight from a table, straight from the calculator, sorry. So, step 1, as always. Find the null and alternative hypotheses. Whenever you do this, okay, your null and alternative hypothesis, you are no longer saying we think that the mean is this or the population proportion is this, and we think with our alternative hypothesis that the mean is greater than, less than, not equal to that particular value, and same with the population proportion. That's what we've dealt with before. But all of that was in normal distribution. What we are now dealing with is our chi-square distribution. And because what we are actually trying to do with a chi-square distribution, as you'll see with the problems that we're going to do, you're always looking at the difference between the expected and the actual values of a particular outcome. So what's the expected number of this particular outcome, and what was the actual number of this particular outcome? Okay. Whenever we do the null hypothesis, you are always going to assume that the stated proportions remain the same and they do not change. So when they've said to you at the top of the problem, we think that this particular thing is going to occur 10% of the time, this particular thing is going to occur 20% of the time, etc. Your null hypothesis is that those proportions remain as they are. So when you conduct this experiment enough times, that thing's going to occur 10% of the time, the next thing's going to occur 20% of the time, etc. Your alternative hypothesis is going to state that those proportions are actually different from what is stated. Okay, so the way that you always do this is you say that the null hypothesis is that the proportions of each outcome remain the same and do not vary. Your alternative hypothesis is that because we've got this other data that said, well, actually this thing really occurred 8% of the time and not 10% of the time, and this other thing actually occurred 25% of the time, not 20% of the time. So because we've had this difference that has happened, we want to test whether in fact these proportions are actually different to what we initially thought they were. Your null and alternative hypotheses are always stated in this way. Your null hypothesis is that your proportions do not vary from what your initial guess was. Your alternative hypothesis is that the proportions do vary because we've got this other data where our actual values were different than what we initially thought. Okay, second part. As always, state the significance level. Okay, as always, is the percentage of the time or the proportion of the time that you want to reject that null hypothesis. So if you've got a significance level of 0.05, you want to reject your null hypothesis 5% of the time. Step 3 is to find the test statistic. Now this is going to look slightly different to what we had before, because everything that we had before, it was dealing with this Z transformation or a T transformation, and it was dealing with proportions and means and all that stuff. What we now have for our test statistic, and bear with me here for a second while I write this out. Okay, what this is saying, we'll go through each step of this. Okay, what this is saying is that let's take the top line. This is taking the actual number of a particular outcome. So this thing happened this many times. This particular outcome happened this many times when you conducted the experiment. So this is the actual number of times that a particular outcome happened. This is the expected number of times that we thought that outcome would happen. So you've got the actual number of times an outcome happened minus the expected number of times that you thought that outcome would happen. So you're taking the difference between the actual and the expected number. You're going to subtract them and then square that difference that you find between the actual and the expected number. What that does is you're basically finding a distance almost. You're just squaring the value to make sure it's positive, as we like to do with distances. You're squaring the value to give you almost like a distance between the actual value and the expected value. Okay? And then you are dividing by the expected number of times that you thought that outcome would happen. Okay? What all that does is it basically scales it down. So you're finding a ratio of the distance with the expected value. So it's just like a scaling factor basically for each one of the outcomes. So you take the distance by taking the difference and squaring it, divided by the expected number of times you thought that outcome would happen. And then you're adding this together for all the outcomes. So as we'll see in a second, we're going to do an example where we have, I think it's 6 outcomes. It's 6 different colours of something that we're looking at. So you would do the actual number minus the expected number for these 6 different outcomes, square it and divide it by the expected number, and then you're going to add that together for all of the 6 outcomes. That is going to be your test statistic. Okay. The other thing that you will need when you do this is you are going to need degrees of freedom. Now, degrees of freedom act very much in the same way as we've done degrees of freedom with the T distribution. Okay, degrees of freedom, if you ever need them, I'm going to call it K this time, K minus 1. It's the number of possible outcomes minus 1. So if you remember before when we were dealing with like means and proportions and that stuff, when we dealt with means, it was always the number of things in the sample minus 1. We're not looking at samples now. We're looking at outcomes. So this time it's the number of outcomes minus 1. Okay? And that's your number of degrees of freedom. All this does with the chi-square distribution, and if you click, because they'll do a way better job of drawing this than I will, if you click on the learn part of 16.2, they have actually drawn out some of these chi-square distributions. What you actually find is it starts off looking somewhat like a normal distribution, but the more degrees of freedom that you have, it's going to look more and more like the normal distribution. The fewer degrees of freedom that you have, the more it's skewed to the right, which means you're going to get this longer right tail. So if you actually have fewer degrees of freedom, so you've got less outcomes, the more it's going to look almost like this, with a longer right tail. Okay, so the less degrees of freedom you have, the more it's going to get skewed to the right. The more degrees of freedom that you have, the more it's going to kind of look like a normal distribution and a bit more centered. Okay, so keep that in mind. It's just a slightly different shape to the normal distribution. Okay, step 4. 2 different things you can do here. Find the critical value or the p-value. Both of these are easy, one's slightly easier than the other, but neither one of these is particularly difficult. If you remember when we did this, you can either compare your critical value and your test statistic. So you see if that test statistic lies in the danger zone. I will tell you now that all of our chi-square problems are always one-tailed. Okay, they're always going to be in that tail. As we saw back here, so they're always, you're going to end up with a one-tailed down here. Okay, you don't really need to worry about that either way, because all you're going to be doing is comparing your critical value to your test statistic, as you could do with that tail. But the much easier way of doing this is to again find the p-value and compare the p-value to that significance level alpha. P-value comes from your calculator, so that one's super easy. If they ask you for a critical value, okay, I would not recommend that you go ahead and find the critical value and compare it to the test statistic and then come up with your conclusion that way. I wouldn't do that, but if they do actually ask you for a critical value, the easiest way of doing this with chi-square, because it does not look like our normal distribution curve, because it is skewed, the easiest way to do it is if you go into Hawks, go into tables. We've looked at one of these tables before. But if you go into tables, on the left-hand side, there should be a tab for chi-square. Okay, if you click on that, all of that table is then for critical values within the chi-square distribution. So what you can do is you pick off your significance level and you pick off the number of degrees of freedom. So whatever your significance level alpha is should come up at the top of, like in the top row. And then it will ask you for the degrees of freedom, which is the number of outcomes minus 1. You match those two up, your significance level with your degrees of freedom, and you go across the table to find the value that is there. That is your critical value. Okay? So the easiest way to do this is to look the critical value up in the table if you need it. If you are doing the whole test where it's not just like, hey, find the critical value, but they actually want you to conduct the whole test, easiest way to do it is we're going to do some stuff in the calculator. You can go ahead and do that and then find the p-value from the calculator. That's the easiest way to actually conduct the test, as always. Okay. So try not to do it the long way. It's just that they may ask you for the test statistic and the critical value. The test statistic we'll see will actually come up on the calculator when you run the test, like we've done with the other tests. Like you'll get a z or a t value that will come up on your calculator as the test statistic. Exactly the same thing here. It's just the critical value that you have to go and find. Easiest way to find it in this case is by using the tables. Okay. Because we've got a one-tailed test here, let's go to our conclusion. So see whether we reject the null hypothesis. Or fail to reject. Okay. As always, you are going to reject the null hypothesis if the test statistic lands in that danger zone. Okay. You would also reject that null hypothesis if p was less than alpha. Okay. So if p is less than alpha, we've talked about this many times before. If p is less than alpha, you reject the null hypothesis. Because this thing is always one-tailed, the other reason that you would reject the null hypothesis is because your test statistic is greater than your critical value. So we call chi-square our test statistic, chi-alpha square is your critical value. This is because, I mean, we've looked at this before, but I've always told you to look in the danger zone. It depends if it's one-tailed, two-tailed, left-tailed, right-tailed, whatever it may be. But because of what the chi-square distribution looks like, everything you do is one-tailed. Which means when you find that critical value, you're actually finding like this value here, chi-alpha square, okay? That means that your test statistic would mean that you would reject the null hypothesis if it fell somewhere over here. That would mean that your test statistic is greater than your critical value. It's just because of what this distribution looks like, because it normally isn't 100% symmetric. Okay, you always end up with a one-tailed test and your tail is always on the right. Okay, so the other reason you would reject the null hypothesis is if your test statistic is greater than your critical value, and it is just because of what the chi-square distribution looks like. So this is the first one of our chi-square problems. And we have a candy company representative that claims that coloured candies are mixed such that each large production batch has precisely the following proportions. So if we were to look at all the candies that are being produced by this company, we would find that 10% were brown, 10% were yellow, 20% were red, 10% were orange, 30% were green, and 20% were blue. What they have then done is they've taken a sample of 353 of these candies and actually recorded how many of those candies there were of each colour. So out of the 353, we have 49 brown, 27 yellow, 99 red, etc. So in that table, we actually have the observed values. The expected values, okay, if we look, we had 353 candies. 10% of them we expect to be brown. So to one decimal place, that would be 35.3 candies should be brown. Okay, we tend to do our expected values to one decimal place. So we would have 35.3 brown, 35.3 yellow, etc. And you would figure out what percentage of 353, so you would have 10% orange as well, okay, stuff like that. You would figure out how many of the candies out of that sample of 353 would be a specific colour. How many would you expect to be a particular colour? That would be your expected value list. Okay, so what you're going to do is you are going to go to your calculator. And what I'm going to do here is I'm going to go to Stat and Edit. And you'll see in list 1, I have put my list of observed values. So that was the list in the table of how many there are of each colour. In list 2, I have figured out each of those percentages of 353. So 10% of 353, 10% of 353, 20%, etc. However many, what proportion there were of each colour, I've actually figured out the number of each colour that we expect to be each certain colour. Okay, so that would be my expected list. This is my observed list. What you're then going to do is you're going to go to Stat, go across to Tests, and if you go to option D, it's the chi-square goodness of fit test, not the chi-square test. The chi-square test is actually what we do in 16.3. But for this one, you want the chi-square goodness of fit test, where you are looking at the difference between an observed value list and an expected value list. So you're going to go to chi-square goodness of fit. Okay, you're going to type in the list for your observed list, which was list 1, that had the list of the observed values in it. List 2 was our expected value list. Degrees of freedom, that is always the number of outcomes minus 1. So in our case, we had 6 different coloured candies. Okay, which means that the degrees of freedom would be 5. It's always the number of outcomes minus 1. Then you're going to calculate. Okay, number up the top is the test statistic. If you were comparing a test statistic to a critical value, that is the number that you would use, that chi-square value. This p-value, in this case, is very small. It's 4.145 times 10 to the negative 23. It's absolutely tiny. And then we have our degrees of freedom. Okay, you can ignore that last list there. So most of the information we need is right at the top. Okay, as always, you're going to compare P to alpha. Okay, so you look at your level of significance and we see that here P is far less than what alpha was. Let's say alpha was 0.1. P is far less than that. Okay, 10 to the negative 23 is a tiny, tiny number. So P is less than alpha, so we reject our null hypothesis. What does that mean? Remember, our null hypothesis states that the proportions are what we thought they would be, that they are what we expected them to be. If you reject that in favour of your alternative hypothesis, that means that you are going with the fact that instead these proportions are different from what you expect. So what we actually observed was far enough off of what we expected that we can instead say that our proportions were different from what we thought they would be. So in this case, we would reject our null hypothesis in favour of the alternative. I also very quickly wanted to take a quick look at this problem. I won't run it all the way through because at the end of the day it's very similar to the one that we just did, but there's a couple of differences with this one in the way that it's phrased. So they've looked at, it's a highway department that looks at the fatal accidents that occur in that state from month to month. So they've looked at the number of fatal accidents in each month from January through December. They have in this study 170 fatal accidents. Now, the null hypothesis in this case would be that the proportion of fatal accidents in each month is the same. So you have a 1 in 12 chance of having a fatal accident on a particular month, which means that you would do 170 divided by 12 would tell you how many accidents you would have in any particular month out of those 170 total accidents. That is how many you would expect each month, because you wouldn't expect from month to month that there would be a huge difference in the number of fatal accidents. So what they would expect you to do in this case is for the observed list, you would have 8, 20, 9, 31, etc. as they have here. For your expected values list, you would actually have all the same number all the way down, because they would expect the same number of accidents in any one month. So you would just do the 170 accidents in this study divided by 12 months would tell you how many of those 170 accidents happened in any particular month. So that's the first thing that I want to talk about. And I also want to talk about the critical value.
So if you ever get asked a question that says, what is the critical value? So you can find the test statistic off of your calculator. If you were doing this the long way around, you would compare the test statistic to the critical value. If it does ask you to find that critical value, you're going to go to tables and you're going to go to chi-square. Okay. Tables is just the quickest way to do this. Trying to do this on a calculator or trying to do this any other way is very difficult, so we always use this. For the particular problem, let's say that my level of significance was 0.1, okay? And if my level of significance is 0.1, and let's say that my degrees of freedom, which is always the number of outcomes minus 1, I think for this particular problem that I'm looking at here, there's 12 different outcomes, there's 12 months. So that would mean that I would have 11 degrees of freedom, and let's say my level of significance was 0.1, so my critical value would be 17.275. So you can always find this straight off of that chi-square table. You just find out what your degrees of freedom are, which is the number of outcomes minus 1, and you look at what the level of significance for that particular test is.